So, hi everyone. As Brian put it, I'm going to talk about why Puffin files can be so important and how they can accelerate the queries that you run on your Iceberg tables. So, a little bit about me. So, my name is Nick Riesanowski. I work on SQL engine optimization and native Python compilation. So, I'm really focused on sort of SQL planner optimizations in order to minimize the amount of compute that needs to be done and to do compute as efficiently as possible. Before that, I got my bachelor's and master's in computer science from UC Berkeley. And I've been working at Bodo for about 4 years, which is primarily where I've been tackling this problem of SQL engine optimization. And I've been working more Iceberg related stuff over about the past year. And I'm currently located in Washington, D.C. I know some people who joined early, we heard a little bit about where you're from. But if you're in the DMV area and you want to like grab coffee or have a chat sometime, please feel free to reach out to me. And I'd be happy to chat with you. So I work at Bodo, and what Bodo is an HPC-based SQL and Python compute engine. So this means that basically we're doing SQL computation, the same as other SQL engines, but we're doing so in a way that uses MPI, so we have more efficient parallelism and multi-node scaling. In addition, we have a JIT compiler, which translates our queries directly to a native binary, and that can lead to optimized performance. And in general, at Bodo, we're focused on compute-intensive queries and really achieving maximum performance on those queries. And this is a natural reason for why we view Iceberg as sort of our preferred table format moving forward, and why when you hear me give this talk, I'm really coming from a perspective of having this information that Puffin files can provide as being so essential to efficient compute. And it's worth noting that if you don't have your data on Iceberg yet, we also support integration with Snowflake, where we treat Snowflake as the I/O layer. We push down just the steps necessary for efficient I/O, and then we do the compute ourselves inside of Bodo. So for this talk, there's three main questions I want to answer. Number one, I want to highlight why Iceberg engines actually need to support Puffin files. And this is actually going to be a good portion of the talk itself in order to really clarify like why this is such an essential problem to solve. Then I'm going to talk a little bit about what Puffin files are and how Bodo actually went about supporting them. And finally, I'm going to talk about what I see as some of the key challenges and the things that make Puffin files not quite yet fully extensible and might be future changes to the Iceberg spec or future improvements to Puffin files in the future. So let's answer that first question as to why Iceberg needs Puffin files. So at its fundamental level, planners have many different options for SQL queries to choose between. If you look at this query that I have on the right here, which is sort of just like a subsection of a sample TPCH query, you can see that there's some arithmetic computation, and then there's a join. And this is sort of one potential implementation, but there's maybe various implementations for how this query could be achieving the same result, but could be structured in different ways. So if you're not familiar with a SQL planner, this is in essence what a SQL planner is doing. It's looking between these many equivalent optimizations and various representations, and it's selecting what it thinks is the best. And it does this by using a mix of heuristics, which might be something where someone who works on planners like myself might say, hey, we're doing a filter. Let's do this filter as early as possible. That's generally a good idea. But it'll also use statistics, and particularly statistics about tables, in order to pick the plan that's actually the best to execute. So in this particular example query, we might be interested in saying, well, should I do this multiplication subtraction before or after the join? Since it only occurs on line item, I could do either. So visually, this is sort of a representation of these two options. On the left, we have the join, then followed by the multiply. On the right, we have the multiplication and the join. And the planner might choose either of these. And how it's going to make this decision really depends on how it's going to minimize what it sees as the cost associated with the plan. So if we look at the one on the left, we basically see that if we're doing this multiplication and subtraction, we're doing it over the size of the output of the join. So if the join were to produce a smaller output than the line item table, it might be preferable to join first and then do the multiplication. But it's also not necessarily always clear. If you also look at this query on the left, you'll see that line item has to load an additional column versus the one on the right because LX extend and discount are collapsed into a single column. And so because of this, the planner is actually weighing multiple decisions here because it also has to consider the cost of the join. And does keeping that extra column around increase the cost of computing this join? And so in effect, this is why we need to make decisions that are based on like more complex calculations of the overall cost of the query, and why we need statistics in order to make really these informed decisions, because they're case-by-case basis. There are several of these optimizations that exist. There are many different ways the planner can change a query. But by far, the most important way is when it comes to join ordering. So here's another sort of example snippet from a TPCH query, where we join the customer table to the orders table, and then afterwards we join the line item table. And if you execute this query as written, what you would do is you would end up joining customers with orders together. and then you join to line item. But a perfectly valid alternative that you may want to do is because you're just joining on order key, you could join orders and line item together first, and then you could join with customer. And because of this option, the planner needs to make a decision about which of these join ordering it wants to choose. And getting this right versus getting this wrong can be orders of magnitude performance. And why the join problem is so hard, there's a variety of reasons. But one of the main conceptual reasons is that joins represent two different things within a plan. So a join can be acting like a filter, where you might use a smaller table to shrink the size of a larger table. And that's what we'd call a filtering join. But by the same notion, the join instead might be an exploding join. It might be a situation where there are a lot of matches, and the output of those matches means that the output is much larger than either of the inputs. And if you encounter those exploding situations, it typically has a very negative impact on performance. So to be able to decide how we want to order these joins, we need an ability to sort of approximate the cost, or how expensive it is to both the compute a join and how big the output of the join is actually going to be. So when we have a join, we might have a condition like a join on order keys. And each table will have a different number of order key values that exist. I'm going to refer to that as sort of like the number of groups. And so if we're trying to predict the size of the output, we potentially care about how many different order key values exist in each of the tables. The join kind of behaves like a filter. So we care about selectivity, how many of those rows are going to match. And then also within groups that are matching, we care about the size, because the exploding property comes from the fact that you don't just select the winner in terms of if you have a match. You output sort of like every row as a combination of both sides. So if order key had value 1 and there were 10 entries in the two tables in line item and order, you would end up with 100 rows in the output for just that one key. And that's why you're going to get an exploding nature. And what we're going to do is we're going to see that if you use the number of distinct values, you can get pretty good information about these components in order to approximate the result of determining the output size of a join. So NDV is directly this number of distinct groups. You get some indication, although not the best indication, of selectivity from the fact that they may or may not be the same. And then you can get an estimate of how big the sizes can be, because you know how many groups there are. So what I'm going to do is I'm going to run through an example that I ran in Bodo. We're going to look at 3 tables. It's going to be very similar to the query that we looked at with TPCH. We're going to have online orders, which is just going to have an order ID. We're going to have total returns, which will have an order ID and a customer. And we're going to say that a customer may have multiple returns with a different order ID. And then we're going to have locations, which will be a customer and we'll say a store address, but a customer can have multiple stores. So it'll be like the customer could be Target and the store addresses could be all the Target locations. So here we're going to look at a query. It's basically the same as the query we had before, but we specified the columns a little differently. So we have online orders joining with total returns based on order ID. And then we're joining that with locations based on customer. So I ran this example, just simple example to generate the impact, not meant to be a benchmark, on Bodo itself. So we have 100 million rows in orders, 2 million rows in returns, and 1 million rows in locations. And I gave NDV values to give us the property that we were going to have a filtering join between online orders and returns, and an exploding join between total returns and locations. And to do this, we have order IDs as unique, half of our returns being online orders, and 50 of our locations per customer and 100 returns per customer. So each match is going to lead to 1,000 rows, 5,000 rows, basically. So if we don't have any NDV information, a planner is forced to basically rely on its heuristics in order to try to decide how it's going to order the joins. So in this particular example, Bodo doesn't have any special heuristics for these kinds of tables. So it's really just going off the idea that joining smaller tables together, if the NDV values are equivalent, is going to give smaller outputs than joining larger tables together. So when we ran this without Puffin files and without any NDV information, we got that it tried to join together locations and total returns because it doesn't know that customers is so duplicated, and it also doesn't know that order IDs is unique. And so because of that information, it incorrectly chooses to join between these smaller tables and ends up producing 100 million rows as the output, and then it's joining that with another 100 million row result. Now, I'm not saying this is how all planners do it. If you have heuristics in your query, if you have different heuristics for your planner, if you have hints in your query, you're not necessarily going to see the same thing. But overall, it's a problematic case because the planner can't make decisions based on the actual data. In contrast, we reran the same result, but we did it where we applied Puffin files. And this let us estimate the NDV information to being close to the actual values that are given. And so from that, it was able to see that total returns and locations is going to blow up to be a huge exploding join. But in contrast, total returns and online orders is filtering and actually might even shrink total returns. And so because of this, after the first join, we're just going to end up outputting 1 million rows. And in doing this, we've both selected cheaper joins, and our final join is going to be cheaper as well. So even though there's still an exploding join, because there has to be to keep the result the same, at the end of the day, we're able to pick the smaller set of joins, and that's going to impact performance. So I ran this simple example just using one core on an EC2 instance with 8 gigabytes of RAM. And I ran this as a create table as query. And I just looked at only the compute time that wasn't spent in IO, so no read or write. And when I was doing this, I found that the version that had the NDV estimates was 3.6 times faster than the version that didn't have the NDV estimates. And furthermore, this is actually a pretty simple case, right? None of the columns that I made were particularly big. I didn't try to do real addresses to blow everything up. And 100 million rows it can be a lot of rows, but I have more than enough RAM to actually store all of this in. So if we're running into situations where this couldn't all go to RAM and it had to spill to disk, we're potentially talking about situations where we're talking about 10, 100x times speed up if you get the join correct versus if you get it wrong. So join order performance is really dependent on having the ability to make smart, educated guesses about which joins should go together. So I do want to note that while join ordering is the most important problem, NDV information actually has impacts throughout the entire plan optimization process. So the first location is other operators sometimes directly depend upon NDV values. So if you have a group by, for example, and you're saying group by customer ID and store, for example, that depends on the NDV information. If you have just a single key and it's group by customer, it's exactly the NDV. If it's 2 columns, it's a function of the NDV. It's not exact. You'd have to approximate and try to make a guess about correlation, but you can use that information in order to make a better guess than if you didn't have it at all. And the same goes for a select distinct. And it's worth noting that there might be situations where you want to have NDV information across groups themselves. And I'm going to talk about that a little bit at the end for how we might want to do that as future work. The next place where this matters is just row counts. Basically, everything inside of planner optimization is dependent upon making guesses about the number of rows that operators are going to produce. And so because of that, it's important to note that we're not using the NDV information to just pick the ordering of the joins. What we're actually doing is we're using the NDV information to both pick which join is going to be more expensive, but also indicate what we think the output size of each join is going to be. And so because of that, if we go back to our first example, where we're trying to say, do we multiply first or do we join first? NDV is directly impacting that because it's making a guess about how big the output of the join is going to be. And that can help us guide that decision of where do we actually want to do this multiplication. And finally, it's worth noting that in most vectorized engines where you're working with hash joins, right? You're running into situations where the 2 tables that are fed into a join, they're not actually the same. Typically, you have a smaller table you'll call the build table, which will be used to produce a hash map. And then you have a larger table that you're able to just stream through. And those are not possible to flip. One of them has to be materialized first. And as a result, if you get the ordering wrong within a join, that can be sometimes as impactful as on performance as getting the join ordering wrong. And for that reason, it's important to note that while this says T1 and T2, if those are immediate tables, it's not directly dependent on NDV. But if there's any query or any component that calculates an intermediate table, we could start getting to multiple joins. Then that NDV information is going to be crucial for determining which size it's going to be, because it's going to depend on row counts. So all of this is kind of background to say, why do we actually need Puffin files? And it comes down to the fact that tables are going to change frequently. So we need statistics that are easy to update frequently. And in particular, we need a cheap way to update the NDV estimation. And the important realization here is that if you do multiple updates to the same table, you can't get NDV information by just looking at the NDV values of those updates. If I insert 1,000 rows into the table twice, I have no way of knowing if the unique values from update 1 completely match the unique values from update 2 or are completely distinct from the unique values in update 2. And so as a result, since this has such a huge error bound, we need a better approach in order to be able to get broader table statistics that can be useful in calculating estimations for our query. And that's going to take us into why we want Puffin files. So let's start with what Puffin files actually are. So at a high level, Puffin files are an Iceberg custom file format that's designed for complex data structures. So you'll hear them talk about being able to represent arbitrary bytes. What is really being stated by this is if you need to be able to represent something like, in our example, it's going to be a sketch, right? And there's no clear way to do that in sort of like a JSON metadata fashion. You need a file format that's extensible so that it can be dumped as a set of raw bytes and then have metadata for how any engine can interpret those bytes. Within each blob, there's an associated list of fields, and these are the columns that it ends up actually pertaining to. So for example, everything that we're going to be doing when we're talking about the NDV values for columns, those are single field examples. We're looking at like just one column and trying to do some calculation based on it. But as I mentioned earlier, you might have like group by customer ID store. In those cases, you can see there might be use cases where in the future you want to have blobs that correspond to multiple fields, and those might be useful. And an important thing to understand about Puffin files is that everything that's inside of a Puffin file is designed to be usable by any possible engine that supports it. So everything down from the library that's implementing the actual sketches in our example to the configuration details, those all have to be specified either directly by the spec or specified as part of the metadata if they're configurable. And for this reason, Puffin files currently only support Theta sketches. And so you're going to hear me talk about Puffin files and kind of use Theta sketches interchangeably for that reason. So what is a Theta sketch? Full disclosure, I'm not a sketch expert. So if you're interested in some of the lowest level details about Theta sketches, I may not be the best person to answer that for you. But at a high level, Theta sketches are an example of a cardinality sketch. And a cardinality sketch is basically a classification of data structures where you're able to approximate the NDV value, not by maintaining the exact set of distinct values, but by using a mix of hashing and sampling on a set of distinct values in order to more compactly represent NDV information within some fixed error bound. So as a general rule, the APIs that are available are going to be update, which is essentially how you insert into one of these sketches. It's going to be union, which is how you combine two sketches together. And there's going to be estimate. And estimate is where you get the actual NDV value. And union here is the real key because it provides us the capabilities to actually be able to look at multiple updates together without looking at all of the file contents. So in our example where we had update 1 and update 2, and we wanted to know the NDV information, what we can do is create a sketch of update 1, then create a sketch of update 2, union the results together, and then only then take the estimate. And that will allow us to avoid that really high error bound that's associated with the information of just looking at the actual NDV values. There's a couple more Theta specific operations that aren't shared by all cardinality sketches. They're basically other set operations, like notably intersection and difference. And these have higher error bounds, but are potentially interesting at looking at different types of joins or some more join implementation details. But I haven't explored those in significant detail, although I'd be happy to talk about them a little bit of how they could be useful if anyone has a question. So now let's get to how you actually use Puffin files. If you're a reader, Puffin file support is really simple. It's really easy, and it's where I think any engine should start. So if you're an engine or you work on an engine right now and you don't have support for reading NDV values when Puffin files exist, I recommend adding it. Basically, it's just a field that's inside of the metadata, and all you have to do is traverse the statistics, check the associated snapshot, look into the blob information, and then match the fields to the corresponding NDV value. It's that simple. You don't need to have any actual knowledge of Theta sketches existing. You just basically need to check the type. If you're going through the process of actually updating Theta sketches, it's a similarly simple concept, but you do actually have to integrate sort of the Theta sketch library that's approved by the configuration into your ecosystem. So what you end up doing is you construct a sketch over the current update. Then you download an older sketch, which you get from the contents of the Puffin file. The library has a way to deserialize that back into a sketch representation. Then you use this union API to combine the sketches together. And finally, you write back the results and you update the metadata in order to get the up-to-date NDV calculation. And so Bodo's implementation follows these steps, except in particular, when we're doing this, we do this as part of our write process. So if you have a create table as query or you have an insert into query, then automatically as part of that write, we're either creating or updating Theta sketches. So in particular, a couple details. So when we do the sketch updates, these are completely trivially parallel implementations. And so when we write out each individual file, we then immediately afterwards go through the process of updating each of our sketches. Then once all of the write steps are done, you can collect all of those sketches onto a single process. You union the sketches together. You write the actual corresponding Puffin file with the up-to-date sketch information. And finally, you update the metadata to make sure the NDV values are up to date. A couple more things about our implementation. So Bodo's engine is written primarily in C++. As a result, we're using an internal data structure that's built off of something very similar and compatible with arrow arrays. And so we had to actually have some integration into Puffin files that's native to C++ that we wrote ourselves. Our update step comes from these arrow arrays, so we work in the actual arrow format for that. And that's potentially relevant because we think that means that a lot of the update information that we're doing generalizes to other engines that'll use arrow, for example. And finally, as I talked about with the union and the actual write step, we haven't optimized this stage because what we saw from sort of just some initial example benchmarking is that this wasn't the critical step. So we ran a simple experiment to try to understand how much overhead is associated with Puffin files. And to do this, what we did is we leveraged the fact that we can read data from Snowflake and then we can write it to Iceberg in order to read the columns from a Snowflake table, go through the process of then writing them back as an entirely new table into Iceberg, and generated data sketches at the same time as we did. So for this, we took 8 columns from a TPCH SF100 example of line item, and we ran it on a 2-core machine with 8 gigs of RAM. And when we did this, we found that there's about 6.6% of the write overhead was spent on the actual Theta sketch update time, or was spent on the Theta sketch time, most of it in the update time. And it's worth noting this doesn't include the read, and if you're doing a real query, this doesn't include any of the compute. And so because of this, while there is some overhead here, we think it's small enough that given the benefits you can get on the read side, it's more than acceptable. A couple things that are also worth noting are that the update time scales with the number of machines that you have working, because this is a parallel operation. And so if you were to say expand to a larger cluster, for example, you would see this update time go down. And the total write time, since it has some IO dependencies, may not scale in the same way. So it actually might become a smaller percentage of your overhead. And the union and Puffin write time itself, that's a function of the number of columns. So for very, very, very large number of columns, it's possible it does become an issue, but we haven't seen any examples that are. And it's also worth noting that when you have sort of specialized encodings, for example, on 4 of our 5 string columns, we use dictionary encoding, which is the process of basically, rather than just representing a column of strings, you have a smaller section of the column that has the strings that are more or less the distinct values and indexing into it. When you have that step, it becomes even cheaper to update the NDV calculations because you're just updating over the small number of values that might be present. And so as a result, low NDV values, which enable these specialized encoding, can also maintain this encoding more cheaply. And so there may be benefits to the runtime side as well. So now I want to talk about what I consider to be sort of like the pressing challenges with getting Puffin files to be useful for a wide variety of Iceberg workloads. So the first challenge that I see is missed sketch updates. So if you're paying attention to what we had in the metadata information, you'll notice that the statistics file is tied to a particular snapshot. And so if I'm writing with Bodo, for example, Bodo, as part of its insert process, is updating that statistics file to get a newer one, and therefore the NDV values remain up to date. But if, for example, I'm using Spark that doesn't have the support yet, then I might find a situation where an older snapshot has NDV information, but I don't have it in my latest snapshot. Now, that's potentially okay, because there's nothing that's preventing you from going back and looking at earlier snapshots, deciding to use that NDV information, or deciding if too many changes have been made to actually use it. But you don't get that for free. If you're Trino, if you're Bodo, if you're Spark, and you want to do that information, you have to introduce logic to decide when you think it's safe to reuse an old NDV value. And so if you get to any more than like a small period of time with a missed update, you're potentially running a risk of having queries that have variable performance because sometimes they're using NDV information and sometimes they're not. And at a fundamental level, this is occurring because you have a writer that doesn't support Puffin files, and therefore updates aren't being maintained. So you have to run a maintenance operation to make sure you got the latest information. Another area that I think could be a potential challenge would be trying to support multiple sketch types. So I've talked about Puffin files as being just data sketches for right now. The natural place where this is going to go is there's going to be other types of data structures that could be represented. And there may be a temptation to represent multiple types of cardinality sketches. For example, HyperLogLog is something probably a lot more people are familiar with than Theta sketches. I know I was, for example. And so one of the core issues is you may have engines that want to support something they're more familiar with or may already be partially integrated. But in doing so, if there's not a clear benefit, this increases the risk of missed updates. So I checked HyperLogLog, for example, to say, hey, could performance be a clear reason that that might be a preference over using Theta sketches? So my simple example, which again is not fully optimized, Theta sketches are actually deployed inside of Bodo, whereas HLL was thrown together for this example. It doesn't show any clear, obvious signs of there being a performance benefit. And so while it's known to use less memory, it's really just a competing option to a Theta sketch. So now, if you're to encounter a situation where, let's say, engine A supports Theta sketches, but engine B supports HLL, you run into situations where because you have uncompatible sketches, you find that you're not able to keep the sketches up to date. So going back to our previous risk of missed updates, now more missed updates can occur because every engine would basically have to support every single possible type of sketch in order to make sure Puffin files remain useful. However, a more fundamental challenge that I don't think has been addressed yet is queries that end up deleting from tables. So these are update queries, these are merge into queries, these are just delete queries, right? And the key challenge is that sketches themselves are append-only data structures. They don't have the ability to delete. And for Theta sketches, since you're tracking the number of distinct values, you also don't know if when you're deleting, if you're deleting every instance of the distinct value. So even if you could do that, it doesn't really solve your problem. But the problem is, if you have a table that has perhaps a ton of deletes going on, and you want to be able to rely on this NDV information, there's the possibility that you're tracking a bunch of rows that have since been deleted. And if that's the case, you may think that there's way more distinct values than actually exist, and therefore the proportion of distinct values relative to the number of rows is going to be too high. And if you want to get around this, you basically have to rescan the entire table. And that's problematic because if we're trying to scale this to huge tables, we can't be rescanning the entire table. Or if we're going to rescan the entire table, we only should do this when we absolutely know we have to. And so I think an important portion of future work is going to be focused on when do we actually need to rescan this whole table, and how can we keep track of additional information to make deletes viable within Puffin files. So a couple things that kind of factor into this is, number one, having the ability to track the number of deleted rows. If you only have a small number of rows that have been deleted, it probably doesn't make sense to bother like throwing away that NDV information. Same as the example where you said maybe there's like one missed update. Now, the challenge here is this isn't the same as saying like how many rows were deleted, because you don't know whether or not like when the sketch was computed, at least as it's currently written, does include those deleted rows because it's from something older, or if it's later, does it like ignore the fact that rows were deleted and still keep those as part of the calculation. But another way that it could also matter is you could delete, millions of records, but only a small number of unique values. And if you have a lot of unique values, then you might find yourself in a situation where you had a huge number of deletes, but it really didn't matter. And so I think there's a variety of different approaches that the community can take here. But I think looking at how we can minimize the impact of delete queries on keeping NDV estimations up to date is going to be a really important area of future work on expanding the function of both Theta sketches and Puffin support. Another challenge that I think is going to be proving to be difficult in the future is going to be with the enabling and disabling of Theta sketches. And really to kind of highlight this, if you decided at any point you want to enable Theta sketches, you potentially have to rescan the entire table, right? That's the penalty you need to pay. There are situations where this absolutely makes sense if you're not tracking NDV information and it can boost the performance of your reads. That's really beneficial, and that's probably worth it. But at the same time, if you have that information up front, it's generally going to be cheaper and it's generally going to be better. And based on our experiments, we think that single field sketches are cheap enough that they can be enabled by default, and they are within Bodo right now. But the minute we start approaching situations where we extend to multiple columns, this becomes really problematic, right? If we go back to our group by example, we go from something that's linear in the number of columns to something that's exponential in the number of columns potentially, because you have to maintain this power set. And if you're doing that, it's clear you can't maintain all of these at the same time. And so then someone has to make decisions about when you have sketches enabled and when you have them disabled. And users can accomplish some of this, but especially when we get to the vast number of group bys that can be existing, it's my belief that these are too complicated in order to make sure that they can be maintained over the entire life cycle of someone's SQL workloads. And so really, I think a focus moving forward as it relates to Puffin files and Theta sketches should be, can we do extra metadata collection so that we can automate this decision whenever possible? So this could be automated by an engine that's the primary writer. This could be automated by a catalog. But fundamentally, this is going to need cross-engine collaboration and probably catalog collaboration as well, so that we can get enough information about when we want to enable and when we want to disable Theta sketches. So like as an example, if group by customer ID and store, if some of your queries work with Spark and some of them work with Bodo, it might be individually, you don't see it often enough to think it would be beneficial. But if you combine the results of across all of your engines, you might find actually, this is used so commonly that it would be a major performance advantage to know exactly how many groups are in this group by, so I can make really intelligent decisions. And so that I think is going to be a really key point of focus and something where I'd like to see continued future work in the future. And this kind of takes me to my last point, which is hopefully I've convinced you that NDV is really important and the ability to estimate sizes is critical to basically any form of SQL query execution. And for this reason, I think you should be putting Puffin file support on your checklist. I heard good things that the Spark engine is going to have support for it. I know Trino has support for it. I know we have support for it. If you're working in another engine, I suggest prioritizing it. Start with read, convince yourself of the benefits, and then go through to implement write. But if you're using an engine and they don't seem to have it on their priority list, I would try to encourage them to make sure that they are taking it seriously, or I would explore engines that do have Puffin file support. What you may hear is that some tools or some engines don't see the need to actually use Puffin files because they maintain their own statistics. And a really important part of this is actually creating more vendor lock-in than you may realize. So for example, I know that like Snowflake has its own statistics that it keeps about every table, including Iceberg tables. But because of this, if you want to have in a situation where you can use multiple different engines to operate on your data sets, well, now what you either need to do is have each one of those engines maintain their own statistics, which adds extra costs because it has to compute all that information, or you have to run into a situation where you just can't use one of them effectively, right? You're basically, everyone can use it, but only one person can use it well. And so as a result, I think a real important priority for Iceberg as a future like growth area is going to be making sure that metadata and statistics aren't just optional, they're really preferred and encouraged by the spec moving forward, and that we make real significant strides in making sure that every engine seeks to be up to date and to provide this metadata and statistics information so users get maximum choice. So thank you. I think that exhausts my presentation. If you have any questions, I'd love to chat with people. And then if, like, let's say we run out of time, feel free to reach out to me on my email or my LinkedIn. I probably respond to LinkedIn a little better than my email.
Amazing presentation, Nick. Just very well laid out all of the information there. I have never understood Puffin quite as well as I do now, and I've been watching Puffin get created from the beginning. And so, great presentation. Just got to say that, and I think people are echoing the same in the chat. This is really eye opening, very cool stuff. And we even got a question from Ryan Blue asking about the delete specifics of like, so if you have there's if you have a delete volume, could you actually count the NDV on those delete rows to better estimate the number of NDVs and maybe use that as like a determinant to, hey, it's refresh or whatever?
Yeah, so I think so. I think it probably depends a little bit on the delete implementation because you do have to read the corresponding rows. But if you, for example, if you know the rows you're deleting, you can keep the NDV information by keeping a sketch, just another Theta sketch for the column in question. And then again, it supports difference, for example. So you can compute that. Well, you actually don't even need set difference because you know that they're all, one's a superset of the other one. But you can look at that smaller set. You can see how many distinct values are there. And if it's like, like 1%, 2%, some really small percentage of the number of distinct values, well, that's kind of within the error bound anyways. So it probably doesn't matter and you don't need to reproduce the result. If on the other hand, it gets to be like a significant percentage of the overall values in the sketch, then you might say, okay, I want to do an actual refresh process and go through the data again. And you could probably do something clever there as well by kind of saying like, okay, what sort of files have, well, it needs a little bit more thought on if you can find ways to iterate through the table without like rescanning everything, because again, you don't have the full set of information. So that's probably an open question as well.
Yeah, that's okay. And I think, by the way, bring these onto the Iceberg sync at some point. I think this is a good thought exercise for a lot of folks who are, implementing on different engines and things like that. Good general conversations to have. So would love to have you maybe at some point come on and explain some stuff there. Cool. Great question here from Steen. At what granularity are Puffin files calculated and stored? One per file, per partition, per table? And I think this is not actually clarified in the documentation to what I'm seeing. So it's something that I should be updating as soon as you answer this for me.
Yes. So right now, from my understanding of the spec, they're just calculated at a table level. There might be an argument for being able to have them at a partition level, but if there are like a bunch of different partitions that could be maintained, truthfully, it would probably be too expensive to update all of the partitions for like any random write. If, for example, though, you had like an active partition because you were like operating like per day on some amount of data, then there could be a justifiable use case for having a partition that you keep up to date for, say, like the current date. But right now, I believe it's just tables.
Yeah, because especially if you could like, by default, it's table or something like that. And then from there, you might have a, setting that could per table, you turn it on at those different granularities. It's good. I don't know if this is the same question. What are your thoughts on partition levels? Oh, partition level stats.
Yeah.
In general, I think.
Yeah. So, I mean, they seem very useful in general. I'm not going to talk about them at the same level of detail because I'm not as familiar with all the specifics. Fundamentally, I think, having stats at partition level seems really beneficial and seems like something that's kind of an essential case to like keep growing. The question there, I think, is just sort of more along the lines of maintainability. Like, how do you know when you need to update them? Do you have this sort of be a maintenance step where you allow them to be a guest? Do they need to be up to date? And if they need to be up to date, is there any risk that you're updating like thousands of partitions at one time and you're putting too much burden on the write step? With the table step, there's a burden of a single update. More caution has to be used when you're talking about writing across partitions.
Very good. Okay. Understanding from the session, operations such as unions should be supported by blobs. I believe we should add this to the Puffin spec. What is your take?
So I think I'd want to clarify exactly what you mean by like operations such as union. So union, if you look at the Puffin spec itself, the data sketch, like it uses the open source data sketches library. That at the API level of the actual Theta sketches has a union operation. So that's what I mean when I'm talking about union capabilities. If we're talking about union in a SQL sense, you can also, take these sketches, carry them with you from a read step, actually union the results together, and use that in order to make inferences about the estimations as well. That's another capability. To be honest, we haven't fully explored that as well because our planner components are a little bit tangential to our runtime. And so we've been mostly just relying on an NDV calculation, but another area of future work for us is actually integrating the sketches into our planner a little bit more.
And I think, based on the library that Iceberg implements at least in the core library of whatever you're using, like if it's PyIceberg, then I don't think we even support Puffin there yet. Maybe we do, I'm not sure. But based on the main Java API, we support some version. And so you should be able to basically support whatever that library supports at that version. Is that a more general way of kind of answering that question?
Potentially. So the challenge is if you're building like an actual SQL engine or SQL planner, you need something you actually probably need the actual sketches if you want to do things that are complicated. Whereas I presented the read as being just the NDV values. There are situations where you can do smarter things potentially if you have the actual sketches.
Okay. And that will exist actually in the reader and writer of the query engine, not even, this is Iceberg's just specifying where you store it, how you store it, but really this is up to the engine at that point to kind of do whatever it needs to do with that library.
Yeah, so Iceberg can tell you where the file is. It can load the information, I believe, on the Java side of the actual blob of bytes. But I think at that point, then you have to pick it up, implement it with the corresponding data sketches library, and then do all the integration steps.
Cool. In case of cherry picking a branch, I'm guessing these are specifics to branches of tables. Are statistics recomputed after merge for the whole, or are the statistics recomputed based only on these partial results?
So I think that would be a little bit independent potentially. So again, that comes down to sort of, depending on the exact specifics, that either comes down to the delete problem, if there's a chance of deleting rows, or if you're only inserting, it shouldn't really matter if you basically compute the result off of just your local section and whatever the table was at the time, and you union it with the state of the table. I would say we don't specifically have support for this right now, so I'm not exactly sure on all of the specifics of the detail in terms of how this would be supported. But in general, I think it really comes down to what core underlying operations you're doing when you're doing that merge step. If there's deletes, you may need to. Gotcha. Okay, thank you, Ryan. I was not as familiar with this. So for people who didn't see it, Ryan says branches aren't intended to be merged. You said you want to do fast forward to swap, so then you would just have computed them over the result of the branch.
Yeah, it's basically just the update later in the set of things. So that's Git analogy there, but yeah, it's basically just a delayed update to the main branch. And when you were saying actually to apply this, have this turned on in general, would that also apply to the branched table then, and you would apply a Theta sketch to that? Or do you I guess that could be a setting as well?
Yeah, I think that gets a little bit complicated into the configuration, and I probably have to dive into some of the details to know what's going on
It
there. But I
also
assume
depends
that
on
would be
how
a
people
setting.
are using branches, right?
Yeah,
So
yeah, and that adds to the complexity of the challenge of like automatically like enabling and disabling sketches, because most likely,
yeah,
if you have them enabled, in one location, you probably want them enabled in the other location, so you don't get like differing behaviors or the inability to
yeah.
update them.
Yeah, only get good performance on the main branch. Okay. I don't see. Oh, wait. No, I do see. When you create Iceberg tables and insert data, you get a .stats file in the metadata folder. Is that the Puffin file?
Yeah, so I don't think the Puffin file names are actually standardized. I know Trino does a .stats file. At least that was my understanding from playing around with it. And Bodo also implements it as a .stats file to be consistent. So yes, I believe so, because these are the statistics file in the metadata. I can't guarantee that every engine will do that because it's not defined to have a specific suffix, but most likely yes.
At this point, I believe that those are the only two. So actually, that's a good question of should we standardize that name so that that's something, should that be something that goes into the spec as well? Another good area of discussion for the Iceberg sync. Okay. I think we're like pretty much at time. But if anybody has like a one last minute question, I think we can hit that as the very last question. If not, Nick, this has been very eye-opening for me, and the way you laid out everything, the examples you gave. Hats off to you. It's was really eye-opening and very valuable information, and glad that we have this in the bank for anybody wanting to learn Puffin.
Well, thank you, Brian. I really appreciate it. And thank you everyone for attending. I hope you enjoyed.